Right, so here's the first question from the fluid mechanics exam that I sat as a first year aerospace engineering student in 2011, 2010, 2011. So this is a question which has three parts, but we're going to ignore the first part because I think part one is just defining what Archimedes principle is. Okay, so right now my students are preparing for the fluid mechanics exam that I'm delivering the module for. So I thought of going through a couple of questions for the fluid mechanics exam that I sat at University of Southampton. Right, so let's read the question as usual and let's see how we can solve it. And of course, if you have any suggestions for any other topics you'd like to see, let me know in the comments. Okay, so we're dealing with a triangular shaped body, which is tethered in a seawater lagoon. Okay, so we're not given any numbers in this question, but we're known that we know the water density is rho. We know the upper tip of this prism is just touching the water surface. And the base, which is side BC of the triangle, is parallel to the free surface. And for the first part, or for the second part of the question, we have to show that the total force on side AC, right? So that's the force acting on this side, like this. And of course, this force is going to be perpendicular on that side. So we have to show that that force is given by this equation here. So that's rho GL. Let's actually write it here. So we have to show that FAC is given by rho G L squared W over square root of 2, where W is the body width, right? So this is the dimension of the prism sort of like into the paper. So if we maybe try to draw this from like an isometric 3D sort of perspective, this is what we would see. So this is how the object actually looks like, more or less. Okay, so this is A, this is B, and this is C. This angle here is 90 degrees. And then we've got this is L, that those are the lengths of the sides. And then W is actually this. Okay, so actually, you know, the water pressure is acting everywhere on this side. Okay, so yeah, and the area of that, and let's actually do the area. So the area of, well, the area of the face corresponding to that AC side is gonna be equal to the area of the rectangle, right? Which is W times this, and this is the same as this side, which is L times square root of 2. Okay, right, you can figure that out with Pythagoras. And that's pretty much it. So let's see how we can actually, well, do that. So to figure that out, first of all, I would write down the equation for hydrostatic pressure. So hydrostatic pressure is going to be, you know, the usual formula is rho gh, where h is the depth. So let me actually draw the diagram again, and this time I will draw out the pressure distribution as well. So the pressure distribution on the AC side, so on this side, looks as follows. So the pressure here is 0, and the pressure here is, well, of course, it's rho gh, right? So the pressure is rho gh. So the pressure distribution is going to look something like this kind of thing. So it's rho gh here, and then it's linearly decreasing all the way to the top, okay, where it starts at 0 at the top at A, and it linearly increases to rho gh at point C. And the force acting on this AC surface, you can actually do this in a few ways, but I'll do it in the quickest way, which is you can either integrate That's the rigorous way of mathematically sound and rigorous way of doing it. But I'll take a shortcut and I'll use the fact that when you integrate, you essentially find the area under a curve. And the area that you're finding is actually the area of this triangle here. So it's the triangle, is the right triangle, whose sides are, well, this solid green line. And then, of course, you also have the side AC. Okay, and this angle is 90 degrees, like that. So what's the area of that triangle? Well, the area of the triangle is just the base times height over 2. So the base is rho gh, right? That's rho gh here, multiplied by the height, which is AC, and then this is divided by 2. So let's put some, not numbers, but let's put some variables in. So rho gh, so h is essentially the depth of point C, right? So the depth of point C is the same as this depth, because this point, which is B, is at the same depth as C. And we know the question tells us that that side, or that depth, or that length is L. So that's going to be rho GL multiplied with AC, and AC is L root 2 over 2. Okay, so the answer for that is rho GL squared root 2 over 2. And that's the first part of the question, because rho GL squared root 2 over 2 is the same as rho GL squared divided by square root of 2. Okay, and that's FAC. And that's how you get 6 marks. Okay, right, now for the second part, or the third part, this one is not difficult, but it involves a few more steps, as you'll see in a second. So here's what it says. By determining the forces acting on each face of the body, okay, so the face well, the body has technically 3 different faces that we're interested in. So it has AB, BC, and AC. Show that the upthrust, show that the upthrust acting on the body does indeed obey Archimedes' principle. So that's one thing. Also, for the second part, if the density of the body is half that of the seawater, so the density of the body, that's the density of the prism, is half that of seawater, find an expression for the vertical component of the tension in that tether, and determine its value if L is 1 and W is 2. So we're given some values here. Okay. Right now, what I should mention actually in case of in the case of FAC, this force that we found is actually per unit width. So to actually find the total force acting, for on the whole surface, all you have to do is just multiply that force, which is per unit width, by W. So maybe I should make a note that this is per unit width here. So the actual FAC that we're interested in is the force per unit width multiplied by width. So that's going to be equal to rho GL squared W over square root of 2. Okay, and this actually looks like the final, like what the question tells us should be the right answer. Okay, so let's actually try to find the forces acting on each side of the prism. So this is our prism, and the first thing to do is finding, let's say, the force acting on this side, which is AB. Okay, so we can apply the same principle as before, which is we look at the pressure distribution. So we have 0 pressure at top, and then the pressure linearly increases all the way to the bottom, where we have rho G times L, like this. So the force acting on AB is equal to the area of that right triangle again, which is 1/2 base times height. The height is rho GL, and the base is, well, the base is rho GL and the height is L, and we multiply this by the width of the prism W. Okay, and that should give us that FAB is 1/2 rho g L squared W. And that's it. That's the force acting on that vertical surface. Now let's also look at the force acting on the bottom surface. So on the bottom surface, the pressure is uniform because obviously all points on this bottom surface are at the same depth with respect to each other because the bottom surface is horizontal. So the pressure acting here is going to be the same as rho GL. So the force acting on side BC, I think it's called, this is going to be rho GL, so pressure times area. What's the area? It's L times W. So that's going to be rho GL squared W. And that's it. That's the force acting on BC. So let's actually find, or let's figure out how the forces combine to create the upthrust. Now, according to Archimedes' principle, the upthrust, so the upthrust force, this equals the density of the water times G and times the volume of the displaced fluid. Okay, so in our case, the volume of the displaced fluid is the volume of the prism. Okay, because it's the entire prism is submerged, so the entire prism is responsible for displacing the water, basically. So if Archimedes' principle holds, what this means is that the forces, all the forces combined, which is FAB, FAC, and FBC, all of them added up together, should give us this upthrust value rho g times V prism. So let's actually expand this a bit further. So this is going to be rho times g. Now the volume of the prism is the volume of this shape right here, which is pretty easy to figure out. So it's the area of this triangle multiplied by W. Okay, so the area of that triangle is just half base times height. So it's L squared over 2 multiplied by W, which gives you the volume. So the whole thing gives you the force, the upthrust. So let's see how those forces, those three forces combined, will give us this. So let me draw a free body diagram again for the prism like this. And I'm gonna draw the forces. I'm not gonna draw the pressure distribution anymore. I'm gonna draw the forces like this. So this is gonna be FAB. This is gonna be FBC, like this. And this one is gonna be FAC. Okay, the length of the arrows doesn't really tell us anything about the magnitudes. I just drew some random lengths for the three forces. Right, now we're interested in the upthrust, which means that the only two forces which contribute to the upthrust are FBC and FAC. Why? Because they're the only forces that have a vertical component, right? FAB is purely horizontal, so it doesn't actually have a vertical component. So FBC and FAC are the only forces we're going to look at. So FBC from earlier, we got it as this. So rho GL squared W, rho GL squared W, and FAC, we did that in the first part of the question, which was this. So rho GL squared W over root 2. So rho GL squared W over square root of 2. Okay. But we're not interested in the entire FAC force. We just care about the vertical component. Okay, so we know this is a right triangle with equal sides, so it means it's an isosceles triangle, and the question even tells us that this angle here and this angle here, they're both 45 degrees, which means that if you try to find the components of this FAC force, the vertical component will have an angle of 45 degrees with respect to the direction of the actual force. So the force that we care about, or the component that we care about for AC, is this FACY. Okay, so FACY is going to be equal to FAC cosine of 45 degrees. Okay, so cosine of 45 degrees, which is going to be FAC. So FAC was rho g L squared W over root 2. Cosine of 45 degrees is root 2 over 2. So we can then just cancel out. So root 2 cancels out with root 2. And we just get 1/2 rho g L squared W. So this component is acting downwards. Okay, FBC is acting upwards, and it's FBC that is responsible for the upthrust in a way. So the vertical component of FAC is opposing FBC, which means that upthrust equals to FBC minus, and this is going to be FAC in the y direction. So FBC is rho GL squared W. So rho GL squared W minus FACY, which is 1/2 rho G L squared W. So the answer is 1/2 rho G L squared W. Now, does this equal the upthrust that comes from the Archimedes principle? It should. So let's see. So we have 1/2 rho G L squared W, and the Archimedes principle tells us that the upthrust is rho times G times the displaced volume. And that is exactly what we have obtained, right? So it's rho G 1/2 L squared W. So Archimedes principle works, which shouldn't really be that surprising. But this question basically asked us to check whether that's the case. Okay, now there's only one more part here, which is finding the vertical component of the tension in the tether. Okay, so let's actually draw that as well. So let's redraw the prism like this. And here's what we have. So we've got four forces technically. Actually, if you think about it, we've got three forces due to the water pressure. Okay, one of them doesn't actually do anything in the vertical direction. So we're just going to consider this one. We're going to consider this one. Okay, we're going to consider also the tension in that tether, which is pointing downwards. And we're also going to consider the weight of the prism, right? Because the prism has a weight as well, and that's going to be mg. Technically, there are four forces, because there's also the force acting on this side, but this one is not relevant to the question, because it's acting in a horizontal direction. Right, and the question is asking us to find the tension in the tether. So let's see how we can do that. First of all, this prism is in equilibrium, or it's in balance, which means that if I add up the forces in the y direction, I should get 0. Okay, so all the forces should cancel each other out. Now, we already found the vertical component of the AC force, and we got that to be, I think, 1/2. So that's FACY. That's the one we're considering. Okay, so I think we got FACY as 1/2 rho GL squared W, if I'm not mistaken. Just quickly check. Yes, that's it. It's this one here. Okay, so if the forces are balancing each other out, let's write out a force balance. So this is what we have. We have FBC, which is acting upwards. Then we have minus FACY, which is acting downwards. Then we have minus the weight, which is also acting downwards. And then we have minus the tension, which is also acting downwards. And the whole thing is going to be equal to 0. So what the question is asking us for is tension. So we can rearrange for tension quite easily. That's going to be tension is FBC minus FACY minus mg. So what I'll do at this point is replace each term with what each term stands for. So tension equals the force acting on BC, which is the bottom surface, that's going to be equal to rho G and then L squared W minus. Then we have 1/2 rho G L squared W. Note also that this is the upthrust. So we could have, forgot about each individual pressure force, and we could have just considered the upthrust straight away. And then this is going to be minus mg. So m is the mass of the prism, and the mass of the prism is the density of the prism multiplied by the area, multiplied by the area of the triangle, and then multiplied by this w. So that's going to be half L squared multiplied by W. So that's the volume of the prism multiplied by G. Now the question tells us that the density of the body is half that of the seawater, which means that this density here, I can rewrite it as equal to rho over 2, where rho is this density, which is the density of the seawater. So this is going to be T equals, so those two terms are both going to become 1/2 rho G L squared W minus, and then rho P is going to be rho over 2, 1/2 L squared W times G. Okay, so we just end up with 1/2 rho G L squared W minus 1 over 4 rho G L squared W. I just rearranged a couple of terms to make the two terms look similar. So the final result is going to be 1 over 4 rho G L squared W. And that's the tension in or the vertical component, at least, of the tension in the tether. And, well, we could also find the value for this. So if we say that the length is 1 meter and the width is 2 meters, so let's say L is 1 meter and the width is 2 meters, then the tension, which is again 1/4 rho G L squared W, this becomes approximately 1 over 4. Okay, for rho, I'll use 1,000, although for seawater it's slightly higher than that, but let's just approximate it to 1,000. G, I'll approximate it to 10. L squared is 1 and W is 2. So this is going to be equal to what? So we can cancel out a couple of things. So the 4 and the 1,000 cancel out, and this is just 250. So it's 250 times 10, which is 2,500, times 2, 5,000 newtons. And that is the tension or the vertical component of the tension in that tether. Okay? And that is, those are 8 marks. So it's slightly more work than what we did for the first part, but it's relatively straightforward. Okay, so this part of the question was actually asking for 2 things. So first of all, we had to show that for this problem, Archimedes' principle works, which it does, thankfully. And for the second part, we had to find the tension, which we did using Newton's second law, essentially. Okay, and that's the end of the question.